All right, today we have a story that, believe it or not, stretches over 300 years. It connects one of the oldest ideas in all of math to the absolute cutting edge of quantum computing. And it all boils down to a question that seems so simple, but has quietly powered centuries of progress.
I mean, really think about that for a second. How do you find one single true average for something that's in constant motion? It feels like a basic question, right? But wrestling with this idea is what unlocked everything from figuring out how planets move to, well, building our entire modern world.
So let's break this down. If I just give you a list of 10 numbers, finding the average is a piece of cake. You just add them up, divide by 10, done. But what about the speed of your car during a road trip? It's never just one number. It's always changing, flowing from one moment to the next. You don't have a neat little list to add up.
And for the greatest minds back in the 17th century, this wasn't just some fun little puzzle. It was a massive roadblock. How could you possibly nail down a single representative value for something that just refuses to sit still? That was the challenge. And then boom, everything changed. In what has to be one of the greatest intellectual leaps in human history, Isaac Newton and Gottfried Wilhelm Leibniz, working completely independently, developed calculus. And with it, they gave us the exact tools we needed to finally crack this problem wide open. So the first piece of this new toolkit is a theorem that makes this really powerful guarantee. It says that for any continuous journey, like our car trip, there has to be at least one single moment, some specific point in time where the car was traveling at its exact average speed. It proves that this true average isn't just some abstract idea. It's a real, actual value that happens.
Now the theorem even gives us the formula to find it. But you see that kind of squiggly S symbol there? That's the integral. And that, right there, was the bottleneck. Calculating that thing, finding what's called the area under the curve, was a total nightmare. It meant adding up an infinite number of impossibly tiny slices. That is, until the second big breakthrough.
And this is the real game changer. The evaluation theorem is, and I'm not exaggerating, maybe the most important theorem in all of calculus. It took that impossibly difficult problem of calculating the integral and turned it into something that is just shockingly simple.
I mean, just look at that. All that crazy complexity on the left, all those infinite slices, it just evaporates. The theorem says that all you have to do is find a related function, the antiderivative, and then just plug in two numbers, the value at the end of your trip and the value at the start. Subtract one from the other, and you're done. This incredibly simple idea unlocked the ability to do everything from calculating the orbits of planets to designing modern bridges.
So, for about 300 years, this was the absolute state of the art. These tools were brilliant. But, the world got a whole lot more complicated. The kinds of problems we're trying to solve today aren't just about the speed of a single car anymore.
The very nature of the question has changed. We've gone from tracking one single object to trying to understand a massive, tangled network of things. We're now dealing with what are called multivariate problems, where we need to find the average behavior of millions of interconnected parts all at once. Think about modeling a financial market or simulating global climate change.
And this is the new wall we've hit. The sheer scale of these modern problems is just overwhelming. The classical tools of Newton and Leibniz, even when we put them on our fastest supercomputers, they just can't keep up. The problems simply got too big for the old toolkit.
And that brings us right here to today, to the absolute frontier of physics and computation. A totally new kind of toolkit is emerging, one that thinks about this problem in a fundamentally different way.
A very recent research paper proposes a quantum algorithm designed to do this exact thing. It's taking that same 300-year-old quest for the average and launching it straight into the quantum realm.
So the thing we're trying to measure now is called a multivariable random variable. Okay, don't let the name scare you off. It sounds complicated, but you can just think of that vector x as a single container, like a giant shopping cart, that holds all 1 million of our interconnected data points at the same time. The goal is to find the average value of the entire cart at once.
So, how in the world does a quantum computer handle this? Well, it runs what the paper calls a complete quantum experiment. The key idea here is a quantum property called superposition. So think of it like this. Instead of a classical computer having to check each of those million data points one by one by one, a quantum computer can look at every single possibility at the exact same time. It encodes all of that messy classical data into one single elegant quantum state.
And here is where the magic happens. Now that all of those possibilities exist at once inside this quantum state, the algorithm uses a special tool called the Grover operator.
And this quote explains it perfectly. It acts like a quantum searchlight. It shines down on this massive sea of simultaneous possibilities, and it makes the signal from the correct average way stronger, way brighter than all the other wrong answers. This lets it zero in on the mean with an efficiency that classical computers can only dream about.
Okay, so let's pull back for a second. The technology has made this incredible leap from pen and paper all the way to quantum circuits. But the fundamental challenge? It's identical. Find the true average of a complex system.
This timeline really lays it all out. The quest started with calculus, just to understand a single moving object, and now it has evolved to using quantum mechanics to understand entire systems with millions of moving parts. It's a direct intellectual line that stretches across 3 centuries.
And really, that's the big takeaway here. The quest itself is timeless. The genius of Newton and Leibniz wasn't just that they found an answer for their time, it's that they framed a fundamental question so perfectly that we are still trying to answer it today, just on a scale they could have never possibly imagined.
It really makes you wonder, doesn't it? As we're building these incredible new technologies, what other centuries-old ideas from math and science are just sitting there, waiting for their moment, ready to provide the key to the next great leap forward?